Hello, everybody. Today we're going to be talking about sample means and margin of error. Margin of error is extremely important when you're talking about statistics. You'll hear oftentimes in the real world people saying, well, it falls within the margin of error. Now, a lot of times people say that because it sounds good, but we want to actually find out what the margin of error is so we understand the numbers behind everything. So this first classwork example, we have Tanya and Raul with this paper bag that has chips, and the only thing we know is that the bag is marked 40% red chips. So they draw a sample of 30 chips, and then they replace them. And every time they draw their 30 chips, they count how many red, and they had 9 red chips the first time they drew them. Then they drew another sample of 30 chips. Now they have 12. They did this 50 times. Now, in the 50 times doing this, they get this dot plot to show what was going on. So this dot plot is pretty normal. And it looks as if they got numbers from like 7 to about 17. I mean, that looks like what they would get. And 10 was the most common. So what was the most common number of chips? 10. And it says, does this seem reasonable? Well, if they're saying in the bag that 40% of the chips are red and they were drawing 30 chips, and you think about that, you get 12 out of 30 is roughly 40%. So 10 is a reasonable number because you're just drawing out of a bag. So 10 is reasonable because 10 is pretty close to 12, and 12 is 40%, and 12 is here. 12 is like right around here. So what number of red chips, if any, never occurred? Well, like I said, this looks like it's going from 7 to about 17, maybe 18, 15, 16, 17, yeah, 18. So anything less than 7 or more than 18 never occurred in the sample. And given an interval that contains likely number of red chips in a sample size of 30, we want to write this as an interval. And when we write things as an interval, we always write it like a conjunction. So 7 less than or equal to x less than or equal to 18. Now we're actually going to change the x, and we're going to start using, so let me just get my eraser nice and skinny. We're actually going to start using P. P means the population proportion, which we've used before, which is a percent. And notice up here we were talking about 40%. So the population proportion would fall, the population that we have would fall between 7 and 18 chips in this particular sample. And do you think the number of red chips in the mystery bag could have come from a sample drawn from a bag with 40%? Yes, because the data is very, very close to normal. So a lot of these questions are repetitious, but they kind of are designed to keep asking you the same thing in a different way so that it starts to become comfortable with how you think when you look at the numbers. So let's look at the next page. There's a bunch of notes and a bunch of important things that you need to know. You can just follow along right now and then maybe print this one page later. Like I've told you before, you really shouldn't print too much. You should really take a lot of notes yourself. But the next page or two where there's a lot of notes, I think you should probably just print these to have. So let's go through what these different words are that you're going to see. Descriptive statistics summarize how the data will look. It's the measures of central tendencies, your mean, median, and mode. And we use this with the dot plot. We use this with the box and whisker. So mean, median, mode, really, really important. Inferential statistics, we use samples to infer properties of the population. So we have samples and we draw conclusions. Now this U I mentioned with the calculator with the normal CDF. This is the population mean. It's called mu. And it means it is the average from the entire population. It is the true mean. It's the true average. Now, you know, most times you can't get a full population. You know, they only do the census every 10 years because it takes them years and years to then crunch the numbers. So, you know, the census would be our mu. And if they just, you know, talked about a random sampling of people, that would be our mean sample. That would be the X bar. Now, as we go through this particular unit, you'll see that the mu and the X bar are interchanged because what we're going to start assuming is that our sample is big enough that it will definitely replicate the population. But these are different symbols, and that's what those different symbols mean technically, but you're going to see them overlapping. Same is true with this. P is the population proportion. It's the decimal value that we have been finding with the normal, with the actual data and the normal curve. So we did this both with the actual data and with the normal curve. We had all those charts with data, and we made our own P. And then we had the theory where they told us this. This is why I've been trying to go pretty slow with the notes in this unit, especially because we're not together. Now the P hat, this little P with the hat on it, is the sample proportion. So again, this is the population, the entire population, and this is the sample. And again, they will sometimes be interchanged. Very rarely, though, do you see the P hat. For the most part, we just use the P. But you never know. Things can show up, and then all of a sudden you'd be confused. So the most important thing about this is when we look at the results of statistics, we want to determine how often we get the same result, or if we get an extreme result. See, this is the thing. A result is unlikely if it occurs less than 5% of the time. And if it occurs more than 5% of the time, we have something that we would call plausible. Now, this would be if we have a small percent, but the percent is above 5%, it is plausible. If we are 5% or less, we are considered unlikely. So you're going to start seeing the word plausible, and we need to know that that is a small percent, which means it could happen just by chance. And it's usually, you know, around 6%, 7%. It's a small percent, and that would be a plausible percent. So let's take a look at some actual data that we use. You know, you guys might remember that First Lady Michelle Obama was really concerned about the way kids were eating, and so this data is actually from some of the statistics that they used. So I thought it would be pretty interesting to use now. Third graders, and what they did is they were looking for the obesity rates in third graders, and we get this chart. So these are sample means. You know, these are, you know, they went to different committees, took 525 samples of 50. So in 525 different schools around the country, they looked at 50 third graders, and this is what they got, you know, in the different places. 3 were obese, 6 were obese, 8 were obese, 17, and so on. So you can probably read these bars yourself, but I just labeled them in case, you know, there was a little confusion, and this way we're all on the same page. So from these 525 samples of 50 kids, we want to do some statistics based upon what we were just talking about. Now, my graph is going to be above. So if you didn't label, stop the video, rewind, put the labels on so you can follow the work. So we want to do a couple of things. We want to, how many samples had a mean weight that is equal to or more than the extreme given weight? Well, the extreme given weight for part A is actually, we want to be less than. I don't know why this one said more than. All right. If the average, if the mean was less than or equal to 60 pounds, or the frequency is 60, we would look at the chart and we would have kids fall within this less than 60. So here at, you have the 3, the 68 from the bars above. So 60 kids have a mean weight less than or equal to 60%. Part B, the average wants to be above 75 pounds. So now we look at, again, above, and we have 42, 42, 21, 9, 3, 4, 5, and that's 126 kids. So that's, there we go, 126 kids. And how many third graders are more than 90 pounds? That would be the 5. That would be that final bar at the end. So that was number 1, the first thing we wanted to know. Now, number 2, what is the probability that the given weight would occur if you randomly picked one sample? All right, so again, there were 525 samples. And if we picked less than or equal to 60 pounds, what we get for A is 60 out of 525. So this would be our population proportion. It would be about 0.11 or 11% of the time we would pick a kid less than or equal to 60 pounds. If we picked a child greater than 75 pounds, that's a bigger proportion because we had 126 out of the 525 samples, and that would be about 24%. And if we randomly picked a child 90 pounds or greater, that would be 5 out of 525, which is less than 1%, is 0.95% if you move the decimal over. So it would be pretty rare to pick a kid 90 pounds or more. Now, if we get to part 3, if we randomly pick a third grade student in the United States, is it plausible or unlikely that we pick one who weighs in the given range? Again, we are unlikely if we are 5% or less. We are plausible if we are a small percent. So if we look at those notes and we think about it, 11% is plausible because it's much more than 5%. B is more than plausible. It's actually, it's reasonable. It's definitely likely. It's more likely. It's plausible, but it definitely falls more towards the likely category because 24, that's almost, 1/4. So that's pretty close. But C, to pick a child 90 pounds or more, that would be very, very unlikely. That is definitely in the less than 5% range. That is definitely unlikely. So less than 5%, it's unlikely. Small percent above 5 would be plausible. And when you're definitely closer to getting towards the mean, you are likely to happen. So this was just an example to think about what these words mean and how we use them. Now here's an example where I would like you to stop the video and I would like you to input group 1 in your list and find, as they're asking you for the mean and the standard deviation, and They're in order so you can see the minimum and the maximum. And I'd like you to then put in group 2 and find the mean and the standard deviation, and then turn the video back on. Now, once you do this, we find that group 1 had a mean of 15.15, and so that would be group 1. And it has a standard deviation of 4.6. We can clearly see the minimum is 6 and the maximum is 25. And from your data, you can also look and see your quartile 1 was 12, or you could have divided your data into 4 equal amounts and you would have found 12. Your median is 15, and that would be because it was right here between 14 and 16. And your quartile 3 was up here at 18. And so if you had to draw a box and whisker, do it above the line. Our second group, group 2, here's our mean, 17.4. Our standard deviation is 4.4. Our minimum is 9. Quartile 1, 15. Median is 18. Quartile 3 is 20. And our maximum is 28. So then we want to do a box and whisker plot. So we do a box and whisker plot. Here's group 1 and here's group 2. So notice I didn't do them on the line. I did them above the line and below the line because I want to compare these two things together. So if we look at the descriptive statistics we have so far, the sample means and the box plot, what does the data suggest? The data suggests that the plants given the synthetic fertilizer grew more than those given the organic. So it definitely suggests that the synthetic fertilizer grew more than the organic. But we cannot be entirely sure because some of the plants that were given organic grew more than some with the synthetic. You know, so we still have this entire amount here that is bigger than this over here because, you know, this is the smaller end, and we definitely have a lot of the blue that's the same or bigger than some of the green. So even though it suggests, we cannot be entirely sure because there's just really not enough information in these small samples. So that's what it says here. So again, these few pages you should absolutely print out just so you have a lot of this important information and not have to write it all out. So there are very sophisticated techniques to probability statistics to determine what portion of variability in data is due to natural causes and what is induced. So you're going to start seeing some things that will say, well, we induced this. So we try to, you know, force something to happen, like organic fertilizer was not induced. That just happens in nature, and synthetic would be the induced. So natural would be organic and synthetic would be induced. But consider just the question of the difference in the sample means. See, this is where we start to get our margin of error when we consider the differences in the sample means. So computer programs will be able to take out two groups of data and randomly scramble them into new groups. They will do this over and over again and calculate the difference in the groups by analyzing the sample mean differences. So we're not going to do that. That would just be crazy. But when we look, if we take the work that we just did and we find our observed, what we found, the difference is 2.25. So from the data we were given and the stats that we just calculated ourselves, we had a difference in our sample means at 2.25, and 2.25 would fall all the way up here. See, this would be a computer-generated experiment, and this would be the actual experiment. So our actual number fell here, where the computer generated all of this. And if we look at where we landed, look at the data list containing the sample mean differences. Given there are 100 differences, what percent of those differences were at or above the observed hour difference that we just found? Well, only 8 of them. So 8%. So our data is plausible, but it's not highly likely. That's telling us that our samples were too small, like we did not do enough work. So we are plausible, but we can't say anything more than that. We're above 5%. That's it. So this is how we get to the margin of error. The margin of error represents an interval from the expected proportion that would not contain any proportions or very few proportions based on the simulated sampling distribution. Well, that just sounds crazy. Basically, the standard deviation, we can calculate ourselves with this formula. If we know our population proportion, then we also know what not 1 minus our population proportion is. And if we were going to do the standard deviation ourselves, we can multiply our population proportion by 1 minus our population proportion, our not, divided by the number of items in our sample, and then take the square root. That would give us our standard deviation. The margin of error falls within the 95% confidence interval that we had discussed prior to this. We want to be within 2 standard deviations of the mean. If we're 2 standard deviations up and 2 standard deviations below, and we're in this green section, we are part of the 95% confidence interval, and our data would be likely to happen. If we are here, this is roughly around 2.5%, and this is 2.5%, we would be unlikely. So above a z-score of 2 would be unlikely. If not, yeah, here close, we're, plausible when we're at the end, but after this, we are unlikely because we would then be in the less than 5% category. So if we look at exercise 7, if the population proportion of females at Union High School is 0.4, what is the standard deviation? All right, well, the proportion of females is 0.4. That means if you're not female, that would give you 0.6. So if I wanted to use this formula and calculate the standard deviation, I would multiply 0.4 times 0.6, hit enter, divide it by 50, hit enter, and then I would put that value in the square root. So you have to be careful with the order of operations in using the formula. So the standard deviation for this would be 0.069. So now if I wanted, okay, they didn't ask me that yet, so let's not go too fast. So now if I say the proportion of males is 0.6, what would this standard deviation be? Well, again, you're either male or you're not male, 0.4, and you actually get the same standard deviation. So right now, this one was just all about practicing the standard deviation. So if you look down the page, here again are more notes on what the standard deviation is and how we find it, either with the whole population or with the sample population. It doesn't matter. We're going to do some of these and practice those in a moment. But in general, for a known population proportion, about 95% of the outcomes of a simulated sampling distribution of a sample proportion will fall within 2 standard deviations. So this would be, if they say a sampling distribution, this would be like a computer generated. So, and then what we're going to look for in a little bit is like, if they give us an actual population proportion, and then we're going to look at the computer generated, and we're going to see, do we fall within the 95% of the sample distribution? And then we're going to know if our work is plausible or if it's not plausible. So here's the mean, plus or minus 2 standard deviations gives us the 95% confidence interval. So this is a really, really important concept. Now, here we have these notes, which are showing us, you know, they could give you the notes and make it look really, really hard. So I wrote it out because I don't want you to get nervous. Here is the standard deviation that we just looked at, that we just calculated. 2 of these would be 2 times the formula. That looks crazy. So this would be the mean minus 2 standard deviations. And here's the population in the middle. And here's the mean plus 2 standard deviations. So this is just a scary way of saying this on the graph. And I don't want you to get confused by it. This and this mean the same thing. And this is the formula for calculating the standard deviation if they just give you a small amount of notes. They don't give you all the data to figure it out yourself. So here, this is the guy. Estimated margin of error. Your margin of error is plus or minus 2 standard deviations. So the minute you know your standard deviation, if you double it, that's your margin of error. So let's do an example or two and see how this works. The simulated distribution of the proportion of red chips in a sample size of 30 was known to be 0.4. So this is something we've already done. So now here's where we're going to start with the notes that we were just thinking about. If I know the P is 0.4, then I know not P is 1 minus 0.4, which is 0.6. And I know that I have a size of 30, so my number is 30. Now, if I look at the dot plot they give me, you know, my 0.4 looks pretty good. It's pretty close to the center. It's a little off, but pretty close in the normal curve. So I could like look at this and think, you know, I got some pretty good data. So if they say, A, use the formula for the standard deviation of the sample proportion to calculate the standard deviation and round to 3 decimal places. So you should try that without me. And now check your work. Did you get 0.089? And hopefully you did. Now they say part B. The distribution for the sample size of 30 is shown below. So now here's another one. How do these 2 distributions compare? The shape is definitely slightly different, like you can see that, but they're both centered close to the 0.4. This one was a little to the left, this one's a little to the right, but since they're both centered close to the 0.4, they should have the same estimated standard deviation. How many values of the sample proportion are within 1 standard deviation? Well, if we now take the standard deviation of 0.089, 1 standard deviation above would be 0.489, a little bit below the 0.5, or 0.4 minus 0.089 would be 1 standard deviation below would be 0.311. So if I were in between, I would be between 0.311, 0.489, 1 standard deviation. My margin of error, my 95% confidence interval would come from going out 2 standard deviations. So if I added another 0.089 to 1, I would get 0.578. And if I subtracted another standard deviation from 0.311, I'd get 0.222. So my 95% confidence interval is running from 0.222 to 0.578. And if I wrote this as a margin of error, my margin of error would be my mean, my 0.4, plus or minus 2 standard deviations, which if I double this, I get 0.178. So this is the confidence interval. This is the margin of error. So be careful which way they want you to write it. They're saying the same thing. They are saying the same thing, but one is asking you to write it as an interval and one is asking for a margin of error. So you definitely want to make sure you write it with the way they want it. So there were only 2 data points outside the confidence interval with this margin of error. And so it kind of looks like you have some pretty good data. So now here's another example. Example 9. Henry and Terrence drew a sample size of 50 from a mystery bag. Henry drew 42 chips and Terrence drew 40. So they both did their own experiment. So find the margins of error for each student. Well, let's talk about Henry and then you try Terrence. You should definitely turn off the video and try to do Terrence then. If I talk about Henry drew 42 chips. 42 out of 50 gives me 0.84. So my population proportion for Henry is 0.84. So 1 minus that would be 0.16. If I were going to find the margin of error for Henry, I would have 0.84 times 0.16, divide that by 50, take the square root, and then double it. That means Henry's margin of error is plus or minus 0.104. So turn off the video and then try Terrence yourself. Okay, welcome back. For Terrence, I got a margin of error of 0.113, and hopefully you did as well. And here's all the work in case you did it. Let's look at number 10. Suppose a random sample size of 100 will be used to estimate the population proportion. Would the estimated margin of error be greater if p hat were 0.4 or 0.5? Support your answers with calculations. Again, you should turn off the video and try this yourself with the formula. The margin of error for 0.4 would be 0.098, and the margin of error for 0.5 would be 0.100. The p hat, the 0.5, is a larger margin of error. So the sample would be larger than a simulated or the population. So the bigger the sample size, the more accurate your data. So this one, so your population proportion of 0.4 was actually better than your 0.5. Would the estimated margin of error of 0.5 or 0.8 support your be better, support your answer with appropriate calculations? Well, I already did the 0.5. The 0.8, I had a much smaller margin of error. I had 0.080. So the margin of error would still be greatest at 0.5. So it looks like your margin of error for this would be better if you were a little below or a little above the 0.5. So then there's the homework. I would like you to maybe just try 1 and 2 for the homework tonight. I don't want you to try more than that. So try 1 and 2. See if you can do it. If you can't, that's okay. We're going to pick up tomorrow where we're leaving off now. But contact me if there's any question. For the most part today, it's really just thinking about everything that we've discussed, thinking about all these notes, letting it sink in. Again, you should only print out the notes after they're all written in, so you're not like wasting a whole lot of paper. And the rest, like all these problems, you should do in your notebook. So you should not have printed out all 11 pages from this packet.